Hello and welcome to Pre-Calculus 20, section 1.5. Today we're going to be studying infinite geometric series. Now, I had a little warm-up for you to do. Here are the answers. I'm not going to talk about these first three, but I will briefly touch upon this. So if we think about what the absolute value brackets mean, that means that even if we have a number that is negative, but still has an absolute value that's less than 1, then it fulfills this inequality right here. For example, if we take something like negative 3/4 and we take the absolute value, then we get positive 3/4, and it is of course less than 1. So this is the number line representing all the values that fit within that inequality. Okay? Notice that we have open circles here because this is just less than, and it's not less than or equal to. When it's equal to, we shade in these circles, as you'll see in the next one. So the absolute value of r is less than or equal to 3. So r can be anywhere from -3, because if r is -3, then the absolute value of r is 3, and this is true. But if r were to be something like -4, even though -4 is less than 3, the absolute value of -4 is not less than 3, because we take this and then it turns into 4, and this is not true. So this is the range that r can fall into, and we have shaded in circles because it includes 3, less than or equal to. Now this number, 8.88 times 10 to the minus 16, it's a very, very, very small number. That is 8.88 with 15 zeros in front of it. So 0.00000 and so on with 15 zeros until you get a few 8s. This number is very small. It's very close to 0 in value. This is a review of the stuff we've been doing over the past couple days, so I'll let you do that on your own. Go ahead and give it a try. Did I put any more on this page? Nope. This is the focus on that I want you to read. Now, this is a very interesting concept. This guy came up with this paradox, and I want you to go ahead and read it. It's kind of fascinating. And then try to answer this question. Where does his argument break down and why? Discuss it amongst yourselves. See if you can draw any conclusions. On the next page, we're going to study the values of r to the power of n. Now, here r is 1/2, and we are raising it to the power of 50. So we're taking a fraction, raising it to a very large power, and you notice that we get a very small number. Again, 8.8 times 10 to the minus 16. This is very close to 0. Again, we take something whose absolute value is less than 1, so a fraction, and we raise it to a very large power, and again we get a very small number, and that will happen for the next two as well. We get very, very small numbers. So this is 1.3 with 22 zeros in front of it. This is 1.5 with 21 zeros in front of it. So even though we're having very large powers here, we're ending up with very small numbers because we're starting with something that's less than 1 with its absolute value. Contrary to that, or on the flip side I guess, the next 4 here, we have numbers whose absolute value is greater than 1 raised to large powers, and we get very, very large numbers. Okay, so 9.2 times 10 to the 206 is 92 with 205 zeros after it. That's a lot of zeros. That's a huge number. So I want you to fill in these on your own, and if you have any trouble doing that, just go ahead and ask me. Okay, you can try this. Try to find the sum of the infinite geometric series. I know you don't have a graphing calculator, so this isn't really going to work for you. But if you use a square, you try to find a sum by continually dividing this in half. Okay, so then we have half of the first half. Now, we have, half of the first page, the first square. So we have half of the whole square. Now if we divide that chunk in half, now we're taking half of that original half. So this shaded region is a quarter of the original square. And then you can keep dividing them in half. So we take this piece and we divide it in half. Now this shaded piece would be 1/8 of the original square, because you'd have 1, 2, 3, 4, and then 5, 6, 7, 8, all equal in size. Okay, and then if we divide that in half, this shaded region, if you were to actually shade it, would be 1/16 of the original square. Okay, keep going for a few more terms. See if it gets you anywhere, or what number you start moving towards. Here's the equation. Find the general sum. Find the sum of the general infinite geometric series having an absolute value of r that is less than 1. And if we start with term 1, I love popcorn. So T1 is the first term in the series. R is the common ratio, just as it was in the previous lesson. And S sub infinite is the sum of the infinite series. Then we can find the sum of an infinite series very simply by taking T1 over 1 minus r. Probably the simplest of the formulas we've looked at so far. So let's try a couple here. Decide whether each infinite geometric series is convergent or divergent. State the sum of the series if it exists. Now, we haven't really come across these words yet. Oh wait, we were supposed to have. There they are. Okay. A series with an infinite number of terms whose sum of partial terms approaches a fixed value is called a convergent series. Now, the word converge means come together. So if you have a bunch of, say if you think about a bunch of lines, they're all coming together to a single point. They're converging. Okay? Now, that means they have a sum. They will approach a fixed value. This one, if they don't have a sum, they never approach a fixed value, then that's called a divergent series. And divergent means they start at a point and they just move further and further away from each other. Okay? And those ones you will never be able to find a sum because they just keep getting larger and larger, or further and further towards negative infinity. So, state the sum of the series if it exists. Now, here the first term is 1, and the common ratio is negative 1/3. Because the absolute value of r is less than 1, so if we take this, 1/3 is less than 1, then that means this is a convergent series. It will approach a specific value. So let's find the sum of that series because it does exist, and we know we can find the sum S sub infinite is T1 over 1 minus r, which means that S sub infinite is 1 divided by 1 minus negative 1/3. Okay? So S sub infinite is 1 divided by 1 plus 1/3. So 3/3 plus 1/3, which is 4/3. So we get 1 divided by 4/3, which when you divide by a fraction, you multiply by its reciprocal, and the answer is 3/4. So that is the sum of that infinite series. Now, it may seem weird that we're starting with the number 1, and then we're finding a sum of 1 plus a whole bunch of numbers, and we end up with something less than 1. But remember, every other term we are going to be subtracting. Okay, so we go 1 minus 1/3, which puts us much less than 1, and then we add only a 9th to come back a little bit. Okay, and then we subtract a little more, so it's going to alternate, and the sum will be less than 1. The sum is 3/4, or 0.75. Now this one, first term is 2, and your common ratio is -2. 2 times -2 is 4, 4 times -2 is 8, sorry, -4, and -4 times -2 is 8. And since this, the absolute value of this is +2, which is not less than 1, this is a divergent series, and it does not have a sum. So we will not be able to find the sum of that one. So here's your turn. Go ahead and give it a try using the same techniques we just used on the last page. So find T1, find R, and then if the absolute value of R is less than 1, go ahead and find the sum. After you come back from hitting pause, the answers will be here waiting for you. So hit pause now. There's your answers. Oops. Oh. Okay. So let's apply this new knowledge. Assume that each shaded square represents 1/4 of the area of the larger square bordering 2 of its adjacent sides. So 2 of its adjacent sides. So this shaded square is 1/4 of the larger square bordering these 2 sides. This shaded square is 1/4 of this larger square bordering 2 of its sides. Write the series of terms that would represent this situation. Okay, so we start off with a big square. We shade 1/4 of it. Now, we take another quarter of that and we shade 1/4 of it. Okay, so we're shading 1/4 of a quarter, and we're adding that blue shaded area to this shaded area. So 1/4 of a quarter is 1/16. Then we're taking this thing that's been divided into quarters, and we're shading just a quarter of it. So we're taking a quarter of a quarter of a quarter, and you can see the trend here that's going to continue, and that will make an infinite series that will go on forever. Hence the word infinite. How much of the total area of the largest square is shaded? Okay, so the largest square, we want to find out. We shaded a quarter, then we shaded a 16th, then we shaded a 64th, then we shaded a 256th, I guess, and so on. So we want to find out how much of this big square is actually shaded blue. So all we have to do is find the sum of all these shaded areas. So the sum of an infinite series, and we know that this is convergent because our common ratio as well as our first term are both, common ratio, are both 1/4. So we start off with 1/4, and your formula says 1 minus r, so 1 minus 1/4. So we have 1/4 divided by 1 minus 1/4 is 4/4 minus 1/4, which is 3/4. Now when you divide by a fraction, take 1/4, multiply by its reciprocal, which is 4/3. And the 4's will cancel, and you will end up with your total infinite sum of 1/3. So 1/3 of the original square ends up getting shaded when you can continue the shading pattern. Oops. Every time, doll, every time. So here's another your turn. So you can go ahead and give it a try. I'll show you the worked solution that I've prepared as soon as you come back. So go ahead and hit pause now. So here's your solution. Now, I've indicated the term 1 and the common ratio is 1 over 1,000. You can verify that by plugging it into your calculator, and therefore your answer is this. So we get to here and we divide, so multiply by the reciprocal, so 5.584 times 1,000 is 584, and divided by 999. There you go. Okay, one last example and then we'll call her quits. A golf ball is dropped from a height of 2 meters and bounces back up half the height from which it falls. How far will it travel in total before coming to a rest? This is an interesting question. So it's dropped from a height of 2 meters. So before it hits the ground the first time, it is going to travel a distance of 2 meters, and then it will strike the ground. Now, before it strikes the ground again, it's going to bounce up to half of its original height, and it will bounce back up to 1 meter. But then it's got to travel all the way back down to the ground, so it will travel another 1 meter. And then it's going to bounce up to half a meter. And then it's got to travel all the way back down to the ground another half a meter. Okay? And it will continue like this. So we start off 2 meters, and then we're going to add 2 meters plus 1 meter plus half a meter plus 1/4 of a meter, and it will continue like that. Now, this, because it doesn't fit in our trend, this can be kept separate, and this looks like a regular infinite series with a starting term T1 and a common ratio R, which is 1/2, which is the height that the golf ball bounces back up to every time. So we leave this 2 separate. The original 2 meters it travels before it originally strikes the ground, and we find the sum of this one, which would be 2, your T1, divided by 1 minus your common ratio, which is 1/2. So we have 2 plus this whole thing. 2 divided by 1 minus 1/2 is 2 divided by 1/2. And 2 plus, so 2 divided by 1/2 is the same as 2 times 2 over 1. So 2 times 2 is 4. And therefore, the golf ball will travel a total of 6 meters before it comes to a rest. That's it for today. See you in class tomorrow.